everyone, welcome to Gate Pass. I am Dr. Poonam and today I am going to take in this video two problems. First problem is related to ideal gas mixture model. So first of all we will study what is an ideal gas mixture model. So what is an ideal gas? An ideal gas is one in which the intermolecular interactions are negligible and the size of the molecule that is very small as compared to the distance between the particles. So there is an equation which you all know, that's an ideal gas law, which best describes the PVT behavior, and that is given as PV is equal to RT, where V I am using is molar volume. That's why you don't see N over here. Okay. Now what I will do is from this equation I will try to derive all the partial molar quantities. When what I am doing is that I am taking gases, ideal gases at temperature T and pressure P. I am mixing them and again forming a mixture at temperature T and pressure P. Okay. Now I am interested in first finding out what will be the partial molar properties of any species I in the mixture. Okay. So let's start by finding out what will be the value of partial molar volume. Okay. So by definition you all know that partial molar volume is nothing but the derivative of the quantity with respect to the number of moles of species I when we are keeping temperature, pressure and the number of moles of all other components constant except I. Okay. Now I am going to substitute the value of Vig, which is nothing but over here this is a mixture volume. Okay. And you also know that if it is a pure species, then also your PVig that will be equal to RT. Okay. So for an ideal gas, for a pure species as well as for a mixture, okay, your molar volume is going to be the same. So what I am going to do now is I am going to substitute my mixture volume value over here. So it is dou N and RT by P by dou Ni by keeping temperature, pressure and Nj constant. Okay. Now since temperature and pressure are constant, this quantity is constant, I can pull it out and I can write RT by P dou N upon dou Ni, and I have to differentiate this at all constant Nj. Since all Nj are kept constant except Ni, which varies, so this derivative essentially reduces to RT by P dou Ni by dou Ni, which is nothing but 1. So RT by P is the value of your partial molar volume. So what we find over here is that for an ideal gas you have mixture molar volume that is equal to pure species molar volume, which is also equal to your partial molar volume of species I in an ideal gas mixture. Okay. So I am going to write this in terms of my pure species molar volume. Okay. So that's what we have found out, that your partial molar volume that is equal to your pure species molar volume. Next we have to find these quantities. For that we are going to use Gibbs theorem, which states that the partial molar property of any species I in an ideal gas mixture when it is at any temperature T and pressure P, that is equal to your pure species property at the same temperature but at the partial pressure of I in the ideal gas mixture. Okay. So I am going to use this in order to calculate my partial molar entropy, enthalpy and Gibbs free energy. Okay. So let's first derive partial molar enthalpy. Okay. So according to this theorem, what I have is HI bar Ig Tp, that is my partial molar enthalpy, that should be equal to my pure species enthalpy at temperature T and partial pressure Pi. But we know for an ideal gas that enthalpy is a function of only temperature and not pressure. Okay. So this thing is essentially equal to your pure species enthalpy at same temperature and pressure as that of mixture. Okay. So that's what I am going to write over here now. So again this is same. Fine. Now let's find out what will be the partial molar entropy. For that we will do a little trick. Okay. You know that for a ideal gas your partial, okay, your for a pure species, you give your change in entropy as the equation is Cp dt by T minus R dP by T. Okay. In this case, when I am using this theorem, temperature is kept constant. So let's say while deriving this, I am keeping temperature constant. So this term vanishes and I am left with dSi Ig, that is equal to minus RdP by P. Okay. Or I can also write this as minus R ln d ln P. Fine. Okay. Now let's integrate this equation from pressure Pi to P. Okay. So if I integrate this equation from Pi to P, what I get is Sig at some temperature Tp minus Si of Ig at T and partial pressure Pi, that is equal to minus R ln of, and what is, okay, I am just putting the limits, so it will be P upon Pi, but partial pressure I know how it is related to total pressure. It is given as Y times Yi times P. Okay, so P gets cancelled, and if I take it in the numerator, then this minus sign also gets absorbed, so I am left with R ln Yi. Okay, now I am rearranging this equation because I am interested in this value, because this value is equal to your partial molar entropy. So I am going to write it Sig at T and Pi, that is nothing but your partial molar entropy of species I, that is equal to pure species entropy at temperature T and P minus R ln Yi. Okay. So I have now calculated this as well. I am going to write this again over here. So what I get is that pure species entropy minus R ln Yi. Okay. So I have calculated now my 3 of the partial molar properties. Next, what I am going to do is I have to find out what is partial molar Gibbs free energy. For that I am going to use the definition. What is G? G is equal to H minus Ts. So equally well, I can write the same equation in terms of partial molar properties as well. So I get this equation minus Ts. Okay. Now plug the value of these two and you end up with an equation which comes out to be, just write everything, and what you will get is Gi Ig plus RT, because T gets multiplied over here, ln of Yi. Okay. So this is your equation which you get for your partial molar Gibbs free energy. Okay. Nothing, we are just using this equation, substituting these values and then again writing in terms of G. So I am going to write over here this equation as well. Okay. So these are now your partial molar properties. Now I am going to write mixture properties using these. How do? I just use the summability rule. So my mixture property Vi, no, it is a mixture property, so I will not be there because I am summing up. Okay. So my partial molar volume I am summing up for all this thing. So it will be summation Yi Vi Ig. Okay. Similarly, H is equal to mixture property, that is equal to summation Yi Hi Ig, and your Sig, that is the entropy of the ideal gas mixture, that is equal to summation Yi Si Ig minus R summation Yi ln Yi, and your G Ig, that is equal to summation Yi Gi Ig plus RT summation Yi ln Yi. Okay. So I have now calculated my mixture properties. Now if I have to find out what is the property change of mixing, see what this means. This means that if you take pure species, okay, in this ratio that is represented by your mole fractions, and you mix them, then your initially what is this? This represents your property, summation of the properties before mixing the various components. Okay, so my property change of mixing essentially will be, if I do this, okay, so this will be 0. I take it over here, this is also equal to 0. If I take this over here and this over here, okay, so now these quantities basically they represent by property change of mixing. What you see is that for an ideal gas mixture, the volume change of mixing is 0, enthalpy change of mixing is 0, your entropy change of mixing is R summation yi ln yi with a negative sign. Okay, keep in mind that yi, since it is less than 1, okay, so this ln yi quantity will be negative. So what will be your entropy change of mixing? It will be positive, as it should happen. Okay, and over here you will see that your Gibbs energy change of mixing, it will be negative, and for any spontaneous process like say mixing, it has to be negative in order to take place. Okay, so these are your property changes of mixing. So once you know this, then there are so many questions which have been asked on these property change of mixing. So you don't have to remember basically all these derivations. The final equations you should remember. These are very important. Okay, these are very important. You should remember these equations. So now let's go to the question which we have to solve in this video. That was the question 39, which appeared in GATE 2021. It asked you that you have a mixture of carbon dioxide and inert gas. The mole fractions are 0.2 and 0.8 respectively, and they have asked you to find out what will be the minimum work required in order to separate this mixture. Okay, so let's go and see how you are going to do it. Okay, so we have an equation for the Gibbs energy change of mixing. If I want to separate this mixture, okay, then in this case I am going opposite. Instead of forming the mixture, I am trying to separate it. So how I will write it? I have to, find out this. Okay, so these are the species which are separated now, and this is the mixture. So I have to find the difference between now it will be reverse of this equation. Okay, because I am separating. Here I am mixing, here I am separating. Okay, so this minus this, then what I will get, the equation for the minimum work which I require for separation will be this much. Okay, and this much work you will have to do in order to separate that mixture. Okay, so now let's just put everything. So it is minus R, 8.314 given, T is 300 Kelvin, and then summation yi ln I, that means 0.2 ln of 0.2 plus 0.8 ln of 0.8. And don't forget that they have asked you the minimum work which is required to separate 100 moles of mixture. So don't forget to multiply this with 100 moles, because here everything you are deriving in the per mole. Okay, so when they have asked you for 100 moles, just multiply with that and your answer will come out in joules, which you can again convert into kilojoules. So divide by 1000 in order to convert it into kilojoules, and your answer will be 124.8 kilojoules. So this much amount of work you will have to do, minimum this much amount of work you will have to do in order to separate your mixture into pure CO2 and pure inert gas. Okay, so next problem which we are going to take is based on ideal solution model. And ideal solution model, basically it is defined based on the framework which was developed for ideal gas mixture model. So in your ideal gas mixture model, we had given the partial molar Gibbs free energy of any species I, that was equal to the pure species Gibbs free energy when it exists as ideal gas at the mixture temperature and pressure plus RT ln yi. That is what we had obtained for the ideal gas mixture. Now based on this equation, now we are going to define ideal solution, and ideal solution is defined as one for which we have the partial molar Gibbs free energy of any species I. Now it is for ideal solution. Okay, that is equal to Gi Tp plus RT ln Xi. Now in this case, this Gibbs free energy, it is taken as the Gibbs free energy of the pure species I at the solution temperature and pressure, but it is in its real physical state, okay, which in the real physical state at which it exists at temperature T and P. And of course this gives quite well your composition dependency, so we are going to retain this term in this form, except that yi is changed to xi, because for solutions we usually denote mole fractions by x, okay. So now I am defining my ideal solution model by this equation, and then I'm going to calculate other partial molar quantities based on this definition, okay. So for that, first I will write down the basic fundamental equation for Gibbs free energy. Since this is a molar quantity, capital G I am using to denote molar quantity, so I am multiplying it with the number of moles. So d and G, that is equal to NV dP minus NS dt plus summation GI bar dNi, okay. Now this is my fundamental equation. Now what I am going to do is I will write down Maxwell equations based on this. So dou of Gi bar by dou P at constant T and N, that is equal to dou of Nv upon dou Ni, which is now at constant P, T and Nj. Because I am taking derivative with respect to I, so I am keeping all Nj constant, J is not equal to I. What is this quantity by definition? That is nothing but your partial molar volume of species I in the solution, okay. Fine. Now let's write another Maxwell relation, which is dou Gi bar upon, now I am going to take derivative with respect to T at constant P and N, and that will be equal to your minus dou Ns by dou Ni, and I am keeping what? T, P and Nj constant, where J is not equal to I. Okay, so these are the two Maxwell relations which I can write from this equation. Now what is this? This is nothing but my minus Si bar, that is my partial molar volume, partial molar entropy of species I, okay. So if I know this equation, I can take the derivative of this equation and come up with the value of the partial molar quantities directly, okay. So that's what I am going to use. Now I am going to differentiate this equation with respect to first P by keeping T and N constant, and next I will differentiate it with respect to T by keeping P and N constant, and then I will get my partial molar volume and partial molar entropy respectively, okay. You can do it on your own, or I will do it in short for you, okay. So dou Gi bar by dou P, I have to take the differential of this. So if I take, since it is done at constant P, so I can write dou Gi, okay, I am going, not this one, sorry, this is for ideal gas, it's creating confusion, so I am going to erase this, okay. I have to differentiate this equation, right, since I have to derive for ideal solution, okay. So dou Gi, dou Gi bar by dou P, okay. So dou Gi bar by dou P, okay, that is equal to, for ideal solution, that is equal to, since temperature is kept constant, so it will be equal to dou Gi by dou P, okay, plus, now I am keeping N also constant, T constant, so derivative of this term will be 0. So what I am left with is only dou Gi by dou P, which is carried out at constant T, okay. Now because this is for pure species, so, and I am just leaving it like that. Now for pure species, if I write down the equation, what is for pure species, I can write down dG is equal to VdP minus SdT, okay. And if I take dou G by dou P, that is equal to nothing but V, okay, from this equation at constant temperature. So what I have is that then my partial molar volume, that is equal to nothing but my pure species volume, okay, for an ideal solution. Fine. Similarly, if I take this again, then I will come up with the equation which gives me my SIID, that is equal to SI minus R ln of Xi. Okay. How? Because if I take it will be dou Gi by dou T at constant P and N. Dou Gi by dou T at constant P, it will be equal to minus S for the pure species, and then again for RT ln Xi, because I am taking it with respect to P constant, so differentiate T once, so what you are left with is R ln Xi. So this is the value which I am getting. Okay, so you have got what? Your partial molar volume and your partial molar entropy for an ideal solution. You already have a partial molar gives free energy for the ideal solution. Now you can also go ahead and try and derive your partial molar enthalpy, and what you will do is just use the definition G is equal to H minus Ts. So H will be equal to G plus Ts. Put those values and find it out, and what you will find is that it is equal to Hi. Okay, so I am leaving that for you to do it because it's very simple. So what I have done is, now using my ideal ideal solution model, I have now derived my partial molar quantities. Next what you do is that you find out solution properties by taking by using summability relation. So again what you have is that for your ideal solution, you have your, let's start writing with GID. So the solution property for an ideal solution, that is equal to summation Xi Gi plus RT summation Xi ln of Xi. Similarly your SID, that will be equal to summation Xi Si minus R summation Xi ln of Xi. Your VID, that is equal to summation Xi Vi. Your HID will be equal to summation Xi Hi. Okay. Now what you will see is that you are ending up with the same type of relations which you got for your ideal gas mixture model, except that your GI SI terms are the value of the properties at the same temperature and pressure, but in their real physical state. So these do not correspond to your ideal gas, but it is defined differently, and instead of Yi's you have all Xi's. Otherwise your equation is same. Okay, so once again we can go ahead and find out the property change of mixing, which is done like this. Okay, so you have your property changes of mixing. Of course there was a negative sign, I forgot. Okay, so the equations are same as your ideal gas mixture model, and you end up with the same type of equation, so they are easy to remember. Now let's do the question which appeared in GATE 2022, in which they said you have 5 moles of liquid benzene. So let's say benzene I am going to denote by B. You have 5 moles of it. Okay, then you have toluene, which is 8 moles, and you have xylene, which is 7 moles. Okay, now they are saying that all of them are mixed at 25 degrees centigrade and 1 bar pressure. Okay, and it's a very straightforward question, because they are saying that assume that all of them mix together to form an ideal solution, and find out what is the total entropy change in joules per Kelvin. Okay, so you have to find the entropy change of mixing in joules per Kelvin. Fine. What is the total number of moles? 20. Keep this in mind. So here N is equal to total number of moles of mixture is 20 moles. Now entropy change of mixing, that is nothing but your delta S. So I am going to find it out as minus R. What is X? Find it out. 5 by 20, 8 by 20 and 7 by 20. So I am going to find out first my mole fractions, which are, okay, 0.25, 0.25 for benzene, 0.4 for toluene, and 0.35 for xylene. Okay, now put this in this equation. Your delta S, that is equal to minus R, now 0.25 ln of 0.25 plus 0.4 ln of 0.4 plus 0.35 ln of 0.35. Okay, so but what is this? This is your entropy change of mixing per mole. So you have to multiply with the number of moles of the mixture. So don't forget to multiply it with 20, otherwise your answer will be wrong. Okay, do this calculation and you get your answer as 179.67. It's not visible. Let me just 179.67 joules per Kelvin. Okay, so this is your question. So what you see over here is that ideal solution model and ideal gas mixture model. The equations you might the derivation might be intimidating, but the final equations are very easy. Final equations are very easy to remember and very easy to apply. The only trap over here is that you might forget to multiply it with the total number of moles while in a haste to apply these equations quickly. Okay, so keep that in mind. Other than that, these are very simple questions. So thanks for watching. If you like this video, please don't forget to subscribe to my channel and like this video and leave a comment if you have any question. Thanks for watching.